let us start a new chapter, magnetic effect of electric current. We are well acquainted with the term electric motor, electric bell, MRI machines. These all machines works on the basis of magnetic effect of electric current. There are many effects of electric current. Electric current is the opposite of the direction of flow of negative charge electrons. It produces heating effect. Heating effect we can see easily in the glowing bulb. Tungsten filament get heated after some times of glowing of bulb. Then second is the chemical effect. We can see if we pass the current electricity through water, it get hydrolyzed and it breaks into hydrogen and oxygen molecules. Then finally is the magnetic effect of electric current. Many examples we have seen: electric bell, MRI, magnetic resonance imaging machines, etc. Magnets, a substance which attracts small pieces of irons and point in north and south direction when suspended freely, is known as magnet. A naturally occurring iron ore, which is called lodestone or magnetite, also behave as a magnet, but it is very weak magnet. The one we see are made from them in artificial way and permanent and strong. Properties of magnet, we can see it has two poles, north and south. Like poles repel each other and unlike poles attract each other. They always exist in pairs of poles. Repulsion is only sure test for the magnet. Magnetic field and field lines. Magnetic field, the region around a magnet where the force of attraction or repulsion can be detected, is called magnetic field. Magnetic field around a magnet can be detected by using a magnetic compass. Magnetic field lines. The magnetic field lines are the part around a magnet along which the north pole of a magnetic compass needle tend to move. The magnetic field lines around a magnet can be observed by sprinkling iron filling around a magnet. It can also be observed by moving a magnetic compass around a magnet. The magnetic field lines emerges as the north pole and merge at the south pole. The magnetic field lines are closer at the poles and magnetic field lines do not intersect each other. The electric current carrying
Let
wire
us do
can
an
produce a
activity to
magnetic
test
field
how
lines.
the electric
This is
current
shown
carrying
in this
wire behaves like a
small clipping.
magnet.
So
We have
press
taken a straight,
freemake.com.
thick copper wire connected to an electric circuit to pass current through it. A compass is placed near the thick copper wire. Here, we are using the compass to detect the magnetic field when the current is passed through the copper wire. Note the orientation of the compass needle. Close the circuit by inserting the plug key. Compass needle deflects as the current starts to flow through the copper wire. Note that the orientation of the needle has changed. This indicates that there is a magnetic field created around the conductor when the current flows through it. Thus, we can conclude that the electric current carrying wire behaves like a magnet.
Download Spark Learning app.
So in a video we have seen that magnetic field due to current carrying conductor is there. If a magnetic compass is placed near a conductor carrying current, the needle is deflected. This shows that conductor carrying current has a magnetic field around it. If the direction of current is from north to south, the deflection of magnetic field is towards the east. And if the direction of current is from south to north, the deflection of needle is towards the west. The magnetic field around a current carrying a straight conductor is in the concentric circles. It can be observed by passing a current carrying straight conductor through a cardboard and sprinkle iron fillings on it. We will get the iron fillings arranged in the direction of magnetic field lines. Right hand thumb rule. The direction of magnetic field around a conductor is given by right hand thumb rule. It states that if a current carrying conductor is held in the right hand such that the thumb pointing in the direction of the current, then the fingers wrap around the conductor shows the direction of magnetic field. Magnetic field due to current in circular loop. When current is passed through a circular conductor or loop, the magnetic field produced is in the form of concentric circles around the conductor. Towards the center, the arc of the circle becomes larger and appear as the straight line. Magnetic field due to current in a solenoid. A solenoid is a circular coil of wire in the shape of a cylinder. When the current flowing through a solenoid, it behaves like a bar magnet. The end of the solenoids behaves like north pole and south pole of the magnet. The magnetic field produced by a solenoid is similar to the magnetic field produced by a bar magnet. The strength of magnetic field depends upon strength of current and the number of turns in the coil. Electromagnets. A strong magnetic field inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. Such a magnet is called electromagnet. If electric current is passed through a wire wound around a piece of soft iron, it behaves like a magnet. Such a magnet is called electromagnet. Force on a conductor carrying current in magnetic field. A.M. Ampere suggested if a current carrying conductor produces a magnetic field and exerts a force on a magnet, then magnet also should exert a force on a current carrying conductor. Example, if an iron rod is suspended horizontally by a wire between poles of a horseshoe-shaped magnet and current is passed through the wire, then the aluminum rod is displaced. If the direction of current is reversed, the direction of displacement is also reversed. The force exerted is maximum if the conductor is perpendicular to the magnetic field. Fleming's left-hand rule. The direction of force, that is motion of a current carrying conductor in a magnetic field, is given by Fleming's left-hand rule. It states that if we hold the thumb, the forefinger and the middle finger of the left hand perpendicular to each other, such that forefinger point in the direction of magnetic field, the middle finger point in the direction of current, and the thumb shows the direction of force of motion of the conductor. Electromagnetic induction. Given by Michael Faraday, it is seen that the motion of a magnet with respect to coil or a change in the magnetic field induces a potential difference in the coil and produce induced current in the coil. This is called electromagnetic induction. Motion of a magnet with respect to coil produce induced current. If a magnet is moved towards or away from the coil of wire connected to a galvanometer, the galvanometer needle shows a deflection. This shows current is induced in the coil due to the motion of the magnet. Second method of producing induced current is change in magnetic field produces induced current. For example, take two coils of wire wound around a cylindrical paper roll. Connect one coil to a battery and other coil to a galvanometer. If current is passed through first coil, The galvanometer needle shows a deflection in the second coil. If the current is disconnected, the needle moves in the opposite direction. This shows that current is induced due to change in the magnetic field of the first coil. The direction of induced current is given by Fleming's right-hand rule. It states that if the thumb, forefinger and middle finger of the right hand is held perpendicular to each other, such that the thumb points in the direction of motion of the conductor, the forefinger points in the direction of the magnetic field, and the middle finger shows the direction of induced current. Electric current is classified into two categories, direct current and alternating current. Direct current or DC, a current that always flow in one direction only, is called direct current. The current we get from a battery is a direct current. Alternating current or AC, a current that reverses its direction periodically, is called alternating current. Most power stations in our country produces alternating current. AC changes direction every 1/100th second and its frequency is 50 Hz. One advantage of alternating current over direct current is that it can be transmitted over long distances without much loss of energy. Domestic electric circuit. Electric power to home is supplied through the mains. It has two wires. One is live wire, that is positive wire with red insulation, and other is neutral wire, negative wire with black insulation, red and black. The potential difference between the two wires is 220 volt. The earth wire with green insulation is connected to a metal plate kept in the ground. Two separate circuits are used. One is of 15 ampere for appliances with high power rating like geysers, AC, etc. and other is 5 ampere for fans, bulb, etc. The different appliances are connected in parallel so that every appliances get equal voltage, and even if one is switched off, the others are not affected. The appliances having metallic body like electric iron, refrigerators, etc., their metallic body is connected to the earth wire so that if there is leakage of current, it passes to earth and prevent the electric shock. Electric fuse. Electric fuse is a safety device used in electric circuits to protect the circuit and appliances from damage due to overloading and short circuit. It is a wire having high resistance and low melting point. If excess current flow through the circuit, the fuse wire melts and break the circuit. Fuse wire is made of metals or alloy of metals like lead, tin, aluminium and copper. Fuse wire is connected in series with the live wire. Overloading. Overloading is caused due to increase in the voltage, or if the live wire and neutral wire come in contact, or if too many appliances are connected to a single socket. It results in overheating of the wires and cause damage to the circuit and the other electrical appliances. Another cause is the short circuit. Short circuit is caused when live wire and neutral wire comes in contact and the current suddenly increases in the circuit. It causes sparks, fire and damage to the circuit and the electrical appliances.